So here's an illustration of the electromagnetic spectrum. And this is a summary of what we've just been talking about. Long wavelength is low frequency, low energy. Short wavelength, high frequency, high energy. So this is the high energy, all bunched up together, and this is low energy. So this graph here is giving us the wavelength in meters. So out here, this radiation here has a wavelength of 1 kilometer. That's on the order of a mile. That is a really long wavelength, right? And then over here, 10 to the minus 13th meters. That's a decimal point and 12 zeros and a 1. That's really, really, really small, right? Right here, kind of in the middle, little tiny band, this is visible light. And so they pull this down and they expand it out so that we can actually see it. So here we see that red light has a wavelength of 750 nanometers. What does nano mean? 10 to the minus 9. So that would be 750 times 10 to the minus 9th meters. That's not in proper scientific notation, but you get the idea. We use nanometers when we're dealing with visible light because it's a unit that gives us nice numbers. It's difficult to work with things like 10 to the minus 12. It just gets awkward. And that's why we have the metric prefixes. So red light has a longer wavelength and violet light has a shorter wavelength. Violet light has more energy than red light. So visible light is this tiny bit in the middle. This is the entire electromagnetic spectrum. So just above visible light in terms of wavelength, longer wavelength, is called infrared radiation. That's coming off the red end, infrared, right? And then we have microwaves. Infrared, this is the sort of radiation. Have you ever been to one of those motels that have the heat lamps in the bathroom? You turn it on, it's like, oh, it's like so warm in here now. It doesn't give off much light, though, does it? It just gives off heat. That's infrared radiation. It's electromagnetic radiation. Not all radiation is going to kill you, okay? So don't be afraid of the word radiation. We're not talking nuclear radiation here. And beyond this is microwaves. That is what is heating your food in the microwave, microwaves. It's just a different wavelength of electromagnetic radiation. And then beyond that, we've got radio waves. And radio waves vary in wavelength a great deal. And if we go the other direction towards shorter wavelengths, more energy, we get ultraviolet radiation. Is that dangerous? It is. It can give you a nasty sunburn. You get enough of it, and it can give you cancer. The energy causes changes in the molecules in your body and messes up how your body works, and then cells start to grow out of control. So ultraviolet radiation, that's just beyond what our eyes can see on the violet side. Beyond that, more energy, shorter wavelength, higher frequency, X-rays. X-rays can be very useful. Find out if you have a broken leg or not. But too much of them can be very dangerous. When we go past that, we get into gamma rays. This is very high energy radiation and very destructive. Yes? Is that the same UV lights as they use for jaundice in newborns? I think it probably is. It's kind of a blue light. I had one who stayed in the NICU under the they call them Billy lights. But obviously it's not intense enough to actually give them a sunburn. But light interacts with matter. And so the particular frequency of those Billy lights interacts with the bilirubin in the baby and allows it to process and get rid of the bilirubin faster. And that's why they put the little funny little eye covering on there and the diaper, and they have all the skin exposed so they can get rid of that jaundice. Anybody else have any questions? You can't see ultraviolet light because it's beyond what our eyes are able to process. So we can't see ultraviolet light, but it's there, right? So then your book has little sections about each of these. Gamma rays. Gamma rays are produced by the sun and the stars and certain unstable atomic nuclei here on Earth. So gamma rays it's a type of radiation that's given off by unstable elements. X-rays. X-rays can go through solid substances, right? That's why they can get a picture of your bone even though it's covered with skin and muscle. Both of these types of radiation can be used in medicine to destroy cancer and for imaging, but they also have the potential for damaging biological molecules. And so, like pretty much everything, within a certain range, they're very useful, and outside that range, they're dangerous. You know, too much water will kill you, too. I know some of you are headed into the healthcare field. This is a really interesting application of science here. So if you've got a tumor, especially if it's like in the middle of your brain where they can't just cut you open and remove it, how do you get rid of the tumor without killing the patient? Well, you can use X-rays or gamma rays to kill the tumor, but it also causes damage to the healthy tissue that it goes through. And so what they do is they will focus multiple beams of radiation on the tumor. And there's a little damage here, and there's a little damage here, and there's a little damage here, but there's a lot more damage on the tumor. And so by aiming several beams at the same place and hitting the tumor gets damaged, and the rest of the tissue is going to be okay. And the idea is that the treatment should be better than not having any treatment at all, right? You don't want the treatment to kill you. Ultraviolet or UV light, that's a component of sunlight that produces sunburn and suntan. Less energetic, but still damaging. Visible light doesn't damage biological molecules. Have you ever wondered, how is it that we see? Have you ever thought about that? How do we see? How can I see through those windows and see a person walking on the sidewalk way over there? How does my brain do that? There are molecules in your eyes that are sensitive to light, and they rearrange in response to light that comes into your eye. And that rearrangement sends signals to your brain, and your brain interprets that to give us vision. I mean, it's really amazing when you start to look into how that works. Infrared, that's heat. If you take a pot off the stove and you put your hand near it, you feel heat, right? That is infrared radiation. You turn on an electric stove and the heating element glows red, right? Well, as it's giving off infrared radiation, it's also giving off a little bit of red light that we can see. Any warm object is giving off infrared light. And so you've heard about night vision technology. That uses infrared radiation instead of visible light. So here's a picture, a normal photograph of a guy with his dogs, and then here's an infrared photograph. And we see that the warmer areas are red and the cooler areas are blue. And look, a dog's nose is cool. There's his nose, it's blue. That's cool. His eyes are red, his ears are red. And this can enable people to see in the dark. Now, can you see everything? No, but you can see warm objects. Could that be useful if you're trying to find, an escaped convict or something who's hiding in the woods? Yeah, it can be really useful. You get a helicopter and you fly over and you're looking for this infrared radiation. And it's hard to hide. Cover yourself in mud. Yeah, or maybe one of those insulated blanket things or something. I mean, it certainly can be done, but most people that commit crimes like that aren't really smart enough and thinking ahead enough to do stuff like that. Because if they were, they could be very successful without being criminals. People steal and stuff because they think it's easier than having a job. But if you're going to be successful as a criminal, you could be successful not being a criminal. Yeah, I'll stop. Okay, microwaves. Microwaves are used in radar and in microwave ovens. Have you ever wondered how your microwave works? I mean, the oven, we understand that. The oven itself is all hot in there, and you put your food in there. Of course it's going to get hot, right? But the microwave, you stick something in there, the food gets hot, but the air isn't really hot. How does that work? Well, microwaves are a frequency of energy that is well absorbed by water molecules. And it causes the water molecules to vibrate more. Vibration of particles is kinetic energy. Average kinetic energy is temperature. So you get the molecules to vibrate more, the temperature goes up. Microwaves work best on foods that contain water. If you put like a piece of dry toast in there or a cracker and microwave it, it's not going to get as hot as something that has some moisture in it. Radio waves, those include the signals for AM and FM radio, cellular telephone signals, television, and other forms of communication. Those are those really long wavelengths, and those can travel very long distances. So, what should you know about this stuff? I would like you to know the order of the different types of energy. And if you think about it a while and look at the chart, it's not that hard to remember. So here's a question. Arrange the three types of electromagnetic radiation, just giving you three of them. Visible light, X-rays, and microwaves, in order of increasing wavelength, increasing frequency, increasing energy per photon. Now, some of these A, B, and C might be easier to answer than others. I think the energy one is easiest to answer. Visible light, X-rays, and microwaves. Which of these is the most dangerous? X-rays, right? X-rays can be good, but you don't want to get that's why they put the lead shield on you when you get dental X-rays, to protect the rest of your body from the X-rays. X-rays have high energy. So X-rays are going to be the highest energy. So increasing, that means we start at the lowest and go to the highest. So X-rays will be at the end. And then there's visible light and microwaves. Which one is more energetic? Visible light. Visible light goes in the middle, and microwaves. Now, microwaves, you might think, well, yeah, but they're in the oven, the microwave oven, and they make food hot. But they only make some food hot because it just resonates at that particular frequency. It doesn't make everything hot. Sunlight. Is there energy in sunlight? I bet there is. I've got solar panels on top of my house. They cut my electric bill. Where's the energy coming from? It's coming from the sunlight. Visible light has energy. Once we get this established, we can figure out the other ones. So let's think about it. We get the energy figured out. Wavelength. Which, is it the long waves that are more energetic or the short ones? The short ones. So high energy, short wavelength. So it's asking for increasing. So I want the short wavelength first. The short wavelength is the one that had the high energy. So it'll be the X-rays, and then the visible, and then the microwaves. The order, wavelength and energy are opposite. And then let's think about frequency. They're all moving at the same speed. So which one's going to pass me more times, more peaks? The one with the really long wavelength or the short wavelength? The short wavelength is going to have a higher frequency. So this is the short wavelength. That's going to have the high frequency. So you can memorize the chart. You don't need to know any numbers, just the order. Or you can think about it. And what I just said out loud there, that's my thought process when I have to answer a question like this. I just think through it. Because you only have so many things that you can retain instantly. And this isn't one of them for me. Any questions?